Yeah. Okay, why don't we start? So first of all, welcome everybody to our first Oxford Quantum Gravity Zoom seminar. We're very happy to have Diandian Wang tell us about ensemble of BCFTs and 3D gravity. So I'm not going to be too rigid, but maybe let's try to do about 50 minutes of the talk and then the rest for questions.
Sounds
So go
great.
ahead.
Well, thank you for inviting me to speak, and also thank you for organizing this online series, which I think is a very good idea. So today I'll be sort of talking about a story that's been going on for a few years, and which is the connection between 3D gravity and ensemble of CFTs. So the new part here will be introducing boundaries for the CFTs, which makes them into BCFTs. And there'll be mostly about a large central charge limit, which corresponds to classical wormholes. And that is based on this paper that came out recently with Zhencheng Wang, postdoc at UIUC, and Zixia Wei, postdoc at Harvard. But I'll also talk a little bit about work to appear with Daniel Jafferis and Liza Rozenberg, who's a PhD student at Harvard. And that will be a story at finite central charge in the sense that the gravity will have a finite Newton's constant. Okay, so here's the outline. I'll give a very brief motivation, and then I'll give a review. It will be brief, but hopefully it'll roughly explain what has been going on. And then I'll start by introducing what are BCFTs, why do we want to study them, and then I'll move on the two parts of the main story, the large C and finite C stories, respectively. Okay, please do interrupt me because I think it's very hard to write down everything in this 1 hour talk coherently, so I probably will try to mention the important key points. If I miss some logical steps, interrupt me and I'll try to fill it in by answering questions. Okay, so the motivation, the big picture here is that we want to understand the Euclidean factorization problem, which is a problem that in almost any dimensions, you can find wormholes that contribute to the gravitational path integral, which connects two more than one asymptotic boundaries. So from the CFT perspective, if you compute the partition function on the union of two surfaces, sigma 1 and sigma 2, you expect that to factorize, or it should factorize if you only have a single CFT. But because of the wormholes, the answer does not agree with the square or the product of the two individual CFT partition functions. So so that's the factorization problem or factorization puzzle. And I'll explain how the ensemble interpretation resolves that. So that was the first motivation. However, at least maybe for me personally, I think this ensemble interpretation in 3D gravity is actually more than a resolution of the factorization problem. So it does resolve that problem, but also you can compute wormhole quantities, etc., in 3D gravity, and they precisely agree with some quantities you can compute from the 2D perspective using conformal bootstrap. So that precise relation is what makes, I guess, 3D gravity more interesting than its high dimensional cousins. So that's one of the other motivation for studying this. And another motivation would be, why do we study BCFT? They already have been very important progress for studying BCFT in the holographic context. But here, so far, most of the work focus on a single BCFT and its bulk deal. So part of what we do is to take that model that gives you good agreement between ADS and BCFT, but now I try to see if that model works if you have an ensemble of BCFTs. So that could be thought of as a test of this proposal. And if it doesn't work, do we need to modify it? And if it does work, why or what makes it work? So finally, from maybe a mathematical point of view, we'll see that the Virasoro TQFT story has an extension once we introduce boundaries. Okay, so a quick review. So one of the very interesting things we now know about 3D gravity is that we can understand the 3D gravity partition functions on some manifolds as computing some ensemble averaged quantities of 2D CFTs. So here is a very classic example, which is a wormhole that connects two spheres. Each of the sphere has three punctures. So this manifold has a topology of a three puncture sphere times an interval. So the blue lines now are conical defects running from one asymptotic boundary to the other. And there's a label for each of the conical defect. Each of the label essentially labels a weight of this corresponding boundary operator, and they also makes the size of the conical defect different if you change the weight. So this should be understood as computing the average quantityCijk squared in an ensemble of CFTs, whereCijk is the OPE coefficient you need to define a CFT for where I, J, and K runs over all the primary operators. So of course, if you computeCijk squared in a single CFT, it should just equal toCijk itself squared. But the fact that there is a connected component to this contribution, to this quantity, is the same as what we were saying earlier about the factorization problem. We have to interpret that as a statistical average so that it does not have to factorize. Of course, if we just take that and suppose that equals some number, maybe it does resolve the factorization problem, but doesn't really do anything else. But what's interesting about the 2D CFT is that you can reproduce the same expression by studying bootstrap of a single CFT, where you probably have to average over some conformal weights of some operators, but you do get some universal asymptotic formula in some limits. So in this perspective, you don't have to consider an ensemble of CFTs, but you do have to do some averaging. So mathematically, maybe it's not too different, but you do get an independent way of getting the same expression. So that is the precise relation I was saying earlier, that you can define two different ways of computing this, and they agree exactly. This story has been extended essentially to the quantum regime using the tool of Virasoro TQFT. So I'm not going to review that, how to define it, etc. But let me just say that it computes the correct, exact 3D gravity partition function, at least on hyperbolic manifolds. So, for example, I've drawn two manifolds here. And on these, where the blue lines are now Wilson lines in the topological quantum field theory, and these should be thought of as the finite C version of the classical wormholes I was talking about earlier. And for example, if we look at one of them, each boundary is a three puncture sphere, and this one would be C, I, M, J, and this would compute a quartic moment of theCijk. We can ask what's the connection of this with the classical wormholes. Naively, we just have to take the large central charge limit of all the expressions and even the manifold itself. So if these lines are below the threshold, they become conical defects. So that would be similar to earlier. However, if they are above the black hole threshold, it's slightly more complicated. So they sort of become tubes that connect the boundaries. So, but that's a technical point we can ignore for now. Before moving on, let me also say that with around the same time of the Virasoro TQFT, a tensor model for 3D gravity was constructed, and the idea is very much related to what I just reviewed about 2D bootstrap, etc. Because this tensor model is constructed essentially using the bootstrap constraints. So what the tensor model does is to treat theCijk as a random tensor and the conformal weights as a random matrix. And then you have to write down a potential for these quantities, and the potential is constructed by squaring some 2D bootstrap constraints. I'll say only a little bit on the next slide, but let me first say that these potential gives you a Virasoro TQFT, at least part of the potential. So that is another way, in some sense, to bottom up construct a Virasoro TQFT. So the connection between Virasoro TQFT and 2D bootstrap, etc., is very much like the story between transcendent theory and WZW models. So so this part I didn't review very carefully, but that is okay, because this will be sort of a later part of the talk. Most of the talk I'll focus on the classical wormholes, which are sort of easier to say and to draw. But let me do quickly say that the way you get a Virasoro TQFT from the potential is to consider bootstrap conditions. So here are the two bootstrap conditions for CFTs. The first one is saying that if you consider 4 points on the sphere, there are two different channels, S and T channel. And the answer have to agree after the different channel expansions. And the second one says, if you consider 1 point function on the torus, doing it in 2 different channels has to agree as well. So Moore and Seiberg essentially showed that these are the only 2 independent bootstrap conditions you have to consider. Once you ensure these, all the other higher points on arbitrary genus, partition function, or correlator have to be will be consistent once these 2 are satisfied. So how to go from these to the TQFT? So this is mostly explained in this paper from last year by Jafferis, Rozenberg, and Wang, where they say, for example, if you square the first constraint, let's focus on the cross term, and that corresponds to taking the inner product with this S block and the T block, and that you can picture it from a 2D perspective, but you can also picture that from a 3D perspective, where these blue lines sort of become Wilson lines in a 3D manifold. And ultimately, that leads to a 6J, what they call 6J manifold in the Virasoro TQFT. So doing this for all the other terms and constraints gives you all the sort of building block manifolds for the TQFT, which you can then glue them together to build more complicated, or in fact arbitrary partition function of arbitrary 3D manifold. So that is sort of the story of this tensor model, which I'll come back later. But let me now actually go back to the more classical picture and sort of start from the easier stories. Any questions so far? Okay. If not, let me now introduce BCFTs. Okay, here's a very brief motivation. Why do you want to study them? First of all, the boundary is not an exotic thing. Is almost a feature of every real-world system. So that is a basic motivation for studying them. But from also, from the string theory perspective, if you want to include open strings, you do need BCFTs on the worldsheet. So that is a very good reason to study them. And also just from maybe the mathematical point of view, introducing the boundaries naively will have boundary degrees of freedom in addition to the bulk degrees of freedom, which is correct. But this is not a separate sector of the theory. So it's not saying after introducing them they have their own dynamics, etc. There is a very non-trivial interplay between the new boundary degrees of freedom and the old bulk degrees of freedom. So that makes sort of the story richer and the mathematical more interesting. But of course, you could say maybe I don't like to study BCFTs because CFTs are already interesting enough. There's a lot to do with just CFTs. Then you can still benefit from working with BCFTs because, for example, you can compute entanglement entropy of a CFT by formulating the problem in terms of BCFTs. In fact, that gives a very precise independent definition of entanglement entropy that can be checked and computed efficiently. And finally, for people following the story of information paradox, the introduction of boundaries for CFTs gives you a way to realize islands in holography in a much easier way. So in this later paper, in the paper mentioned here, that gives you a conceptual tool to understand the islands.
Actually, Daniel, I have a question
Yes.
about that. I know it's not the subject of your work, but the story with the islands, is that true that the BCFT appears as a single BCFT? Like what I remember is they were computing the entanglement entropy of an interval in a single BCFT with a lot of degrees of freedom at the boundary. And that produced a formula consistent with the island formula. And the point is, I'm just trying to say that in that story, there was a BCFT, but no averaging, right? Is that correct?
Yeah, that's a great question. So this difference is a little subtle because they do have replica wormholes. So you could say that it's not a single CFT. So mathematically, maybe it does involve more than one. But I would say the physics is different because ultimately it is computing the quantity of a single CFT, and also in that story you don't compute you don't see an ensemble averaged quantity being computed. Rather, it is the Riemann entropy being computed. So that is a small, maybe technically important difference.
Right. Okay, maybe I'll ask this, maybe follow up a bit later, but yeah, go ahead.
Yeah. Okay. Yeah. Thanks. So let me introduce the BCFT data because those are the fundamental objects we have to work with. First of all, there's the regional, the old bulk conformal weights labeled by I for the bulk operators, small I. But now we have new spectrum of boundary operators which live on the boundaries of our CFTs. So we'll label these by a capital I. That's just a convention. But we do now only have one conformal weight rather than H and H bar. That is because on the boundary, you can at most preserve half of the regional Virasoro times Virasoro symmetry. So with one Virasoro symmetry group, you only have one conformal dimension. And then we have the same, the old CIJK OPE. We'll call them bulk OPE because that's what happens when you take two bulk operators to each other. But now you will also have the analog of that, which is when you take two boundary operators to each other, you get a boundary OPE. But perhaps what's interesting is that in addition, you have a bulk boundary OPE, which is what happens if you take a bulk operator I to the boundary, where now it can be expanded as a sum over boundary operators and its descendants. and that is called the bulk boundary OPE, and that is sort of the interplay between bulk and boundary degrees of freedom. So we essentially, these are the set of data we need, and we essentially just need to compute correlators of these objects. So previously we had Cij squared. We can now compute Bij squared, Dii squared, or even CBDDD, for example. So there will be correlators among these different types of data, because it is sort of an ensemble that mixes these degrees of freedom. Pictorially, these are the three types of OPE data we just reviewed. Maybe it's useful to notice that we have these little ABC indices in brackets for B and D, and those are just different boundary conditions we can put on these boundary intervals. So the Cijk is like the 3-point function on the sphere. The Bij is a 3-boundary operator on the disk, but each interval can have a different boundary condition. That's why we have an ABC here. And the Dii is one bulk point and one boundary point on the disk, where this disk now can have a boundary condition A, which we can choose. So that was the review of the data. With the data, we can now define the bootstrap conditions. These are similar to CFT bootstrap. In fact, the first two are the bootstrap for CFT we reviewed, but now there are 4 additional ones. I'm not going to explain each of them, but the idea is the same as before, which is if we look at a particular endpoint function, we can expand it in 2 different channels, and they have to agree. And the fact that there are these 6 independent bootstrap conditions will ultimately ensure that whatever correlator you compute on a general surface with n number of bulk operators and m boundary operators on the genus G surface, they have to be independent of how you do the computation. So these are the minimum set of 6 independent conditions. So let me just maybe introduce one of them. The third one here is when you consider 4 points on the disk, where you can now try to do it in 2 different channels, and they have to agree. This is the boundary crossing symmetry. Maybe I'll just say another example. The 5th bootstrap condition here is that if you consider 2 bulk operators, the blue dots here, and the 1 boundary operator, the red circle, you can do it by first fusing the 2 bulk operators using the bulk OPE, and then take that to the boundary using the bulk boundary OPE. Or you can do it by first taking each of them to the boundary by using the bulk boundary OPE, so you get 2 Ds, and finally using the boundary OPE to fuse those 2 with the external operator I. So that's another condition. These conditions are very complicated, but the conceptual part is the same. And so maybe I should say 2 important things about why we need these bootstrap conditions. And the first one is essentially that using these bootstrap, we can compute universal formula for the OPE coefficients. Just like earlier, we were saying that the 3D gravity wormhole, they compute some answer that's exactly the same as some expression you obtain from bootstrap. So these are the analog of that bootstrap results, but for BCFTs. But another point about why we need these is essentially that we'll construct a tensor model analogous to the one reviewed earlier by squaring these constraints. And I'll say that later.
Can I ask you a question?
Yes.
What's the status of the solutions to this kind of bootstrap? It looks much more complicated, right, than the one without the boundaries. So even without boundaries, when you have irrational CFTs, right? I think Louisville is the only known solution, is that right?
For irrational ones, probably I actually don't think there's. I don't know much about the solutions to this bootstrap, especially in the irrational case. But in the rational case, it has been studied to a lot of depth, where they take, for example, the minimum models. They take some WZW models where they know what the bulk data are, and then try to sort of see how would you add the boundary data so that the bootstrap is satisfied. So that was sort of the way they do it, and you could do it for Liza model, etc.
Right. Yeah. So I believe that, yeah, for the rational case, they have solutions.
Yeah.
But I'm just curious if the Simologikovs gave like a solution of the boundary bootstrap as well as the bulk one, like these old papers of where they first kind of, when people say they solved Liouville's theory, do they mean they solved both the bulk and the boundary bootstrap, or they just mean?
Oh yes. So with if you're talking about Liouville with boundary, for example, then they have these boundary conditions, which we now call ZZ boundary condition, FZZT boundary conditions, and then they do solve the boundary OPE coefficients and bulk boundary OPE coefficients, etc. So that's in
But did they
Liouville.
really check? Because I feel like someone told me once, did they really check all these relations? That seems very difficult. Like
Yeah, I would say essentially yes, because that's how they obtain those expressions. Once you check some of them, the other one, once you obtain the formula using some of them, the other one you can check.
Okay.
Yeah. Yeah, but it's probably true that it is more subtle, and I haven't looked into this too carefully. Yeah, but presumably, boundary Liouville theory is has been carefully studied. With certain boundary conditions, you get all the data and OP coefficients, bootstrapped, and you can check everything.
Okay. All right. Thank you.
Yeah, no worries. So before I jump to the new work, another very important thing I should review is the G function. So the G function is, when you might think that if you compute the partition function on the sphere, it's sort of not very physical, it's a normalization. So then you might expect the same for partition function on the disk. But in fact, if you consider partition function on the disk in BCFT, that turns out to be a very physical and important quantity called the G function. So you can think of that within some normalization, you can think of that as the disk one-point function, a one bulk, one boundary point function, which is dii. But now you take both I to be the identity, and that is also a way to write down the G function. And in fact, the G function has a subscript A, which is the boundary condition label we saw earlier, because you can put different boundary conditions on the boundary of the disk, and they give you different G functions. But let me now just pick some particular boundary condition, and then I have a particular G. And then in ADS BCFT, the way this G function is realized in the bulk is proposed by Takanagi to be given by this particular model, where you add a brane, end of the world brane, with a particular action, this extrinsic curvature minus the tension, so that you can tune the tension to agree, or to make it into a one parameter family of solutions, and then equating the partition function of the bulk and the boundary, which is the G function, you get a relation between these two quantities. So in other words, by introducing a parameter T in the bulk theory, you now can engineer it so that it reproduces the G dependence of the disk partition function on the boundary. We'll say more about this, because maybe I'll just raise the puzzle here. This is true for one boundary, because in other words, whatever action you have, you can essentially, as long as you have one parameter here in the bulk, you can essentially equate the action of that one parameter family of solutions to the G function. So the relation will be determined by working out the solutions, but you don't actually have to have a very special bulk action for the brane. But the same is no longer true if you have more than one boundaries, because in that case, the bulk solution is already fixed by once you fix this relation between G and T. So now, if you have multiple boundaries and higher genus wormholes, the question of whether you can still reproduce the G dependence from the bulk is less clear, because you no longer have this free parameter to tune. So that's the sort of the puzzle I'll try to answer later.
Right. Is this multiple boundaries? The two sense of the boundary, right? Is it multiple boundaries for the BCFT or multiple boundaries for the bulk?
I was thinking of multiple boundary for the bulk, but it's actually both, I guess, because as soon as you have multiple boundary for the boundary, you already have a similar problem.
Okay. All right.
So here is, in other words, you have one single boundary for the boundary CFT and a single boundary CFT. You can essentially pick this T in a way so that it gives you the correct answer. That fixes relation, but once you have more complicated setup, it's not clear why this relation still guarantees this correct G dependence from you expect from the boundary CFT. That's the puzzle.
Yeah.
I'll say more about this later, but let me go over now. Move on to the new result, which is first at large central charge. So first of all, we need to introduce more ingredients in the bulk 3D gravity model in order to make the story interesting and to match some results from BCFT bootstrap results. So the model here will have all these ingredients: the usual bulk action, the usual conical defect action already considered in previous work. And the brane action is essentially the one I mentioned earlier in the ADS BCFT literature. But I guess what is new is that you have both of them together, but also you want to introduce some kink, which is, if you look at the picture on the bottom left, is something defect, one-dimensional defect on the two-dimensional end of the word brane, where the end of the word brane here is not smooth. So that's why we call it a kink. And we also can have an object called a puncture, which is when you have a conical defect, it can go from asymptotic boundary, which in this case, the bottom right picture, you have you have a disk with one point function, and that point can go from the asymptotic boundary, it goes inward, and it can end on some end of the word brane, where the brane would now have a puncture. And these are the new objects, and the question or the claim, I guess, we have is, with this model, you just have to find all the wormholes with these ingredients in it for whatever quantities you want to compute on the BCFT side or the ensemble of BCFT. And they should exactly reproduce expressions you can obtain using BCFT bootstrap. So that's a claim. And that claim is essentially correct up to some minor things we couldn't prove precisely. I'll say what. But that claim is essentially...
Sorry, before you go on, back the upper left, I'm a little bit confused. I understood the other three. The upper left picture, the sphere, is that the boundary manifold, in which case there is no boundary in the boundary CFT?
Yes, in this case is Euclidean ADS, say, and you can have a conical defect from one point to the other. So the boundary here is a sphere. So there's no BCFT.
Okay, that's just the old story. That's just a 2-point function of the sphere.
Yes.
Okay, yeah.
Yes. Yeah. I should say, sometimes I refer to BCFT as a CFT with boundary, but sometimes I also refer to BCFT as CFT that can have boundary, and it doesn't have to have a boundary because that's also the CFT old story is part of the new story. That's what I'm saying.
Yeah, and can you just explain the puncture that goes into the bottom right picture? So that's just a conical defect connecting the boundary and the brane. Is that the idea?
Yes.
Conical define. Yeah. Okay.
Yes. From the holographic point of view, this computes the one point function on the disk, and that is a non-zero quantity. And
what's the puncture? Yeah. What's a puncture on a brane? Like from the bulk point of view, what does a puncture mean? I know it's
defect, so on the
like,
brane is actually just a conical defect on the brane. So conical defect is codimension 2 objects. So on the brane, which is already 2 dimension, the puncture is just a point. And if you go around that point, you have a conical angle.
Okay, that's true even though it's fluctuate. Yeah, okay, I see. The brane is fluctuating though, right? The brane is not. It's a dynamical brane.
It's exactly. Yes.
Okay. Yeah.
Yes. Yeah, so all these objects are dynamical. I didn't write down the action, but of course, you need the correct action if you want this to agree with boundary. You could say that I start with some arbitrary, action for these objects, and most of them wouldn't agree. And you have to engineer it in a way that it happens to agree with the boundary bootstrap expression.
I see. Okay.
Yeah.
Thanks.
Yeah, in certain sense that even 3D pure gravity is it's not unique, of course, because as far as bootstrap is concerned, you can have some maybe different theory for 3D gravity, and that could still agree with bootstrap expressions, but not arbitrary theories, because you can write down some terrible theory and that wouldn't agree.
Okay.
Yeah. Okay, so very simple wormholes can be constructed very easily. For example, we can, it doesn't matter how we construct it, but there exists wormholes like these two. And the first one connects to disks, each with 3 boundary operators. And in the bulk, what this become is that each boundary operator is connected, each pair of boundary operator is connected by a kink. These are red lines. And each interval, which we said earlier that each interval can have different boundary conditions. So say A, B, and C. And in the bulk, they become different branes with different tension. Remember the relation between G function and the tension is given by this expression here. So here, if they have different boundary condition, they would have different G function corresponding to different brane tension. So this is object that has 3 different branes, and each of them smooth but connected at some non-smooth kink, and each of them having a different tension. So this is it's a very simple object, but of course it's non-trivial to see why it has exactly the correct G function dependence, etc., to agree with the boundary. And the other one is similar. You have one conical defect and one kink on the brane. These are the simplest wormholes we can obtain. Let me just claim, without going into the detail, that in fact, the action earlier, is, in particular, the brane action is the one from the ADS BCFT literature, this particular one. It does give you exactly the correct G dependence you want from the boundary point of view. In other words, in some sense, we know what we want from the boundary point of view, because you can write down the expressions and, roughly speaking, count the number of G factors we want. And we have to reproduce that for arbitrary complicated wormhole in the bulk. And the reason why it actually works is that we can, for example, when the brane action is positive, we can first work out the bulk solution without tension. So, for example, this picture here is half of the Euclidean ADS, we can glue it to a wedge, and then we just have to show that by gluing to the wedge to it, how much does the action change? For example, another example would be we have a wormhole connecting two disks with zero tension, and now we can glue it to this sort of wedge cross S1, sort of wrap it around this cylinder to obtain the positive tension wormhole. I guess I'm not going to explain this too carefully because of time. So I will just say that it turns out it works precisely, and in fact, it works for arbitrary general wormholes, which we can obtain using sort of a doubling trick. And in other words, we can obtain some very complicated wormholes, and then after doing some doubling trick and taking some quotient, and then gluing sort of wedges like this to it, and then show that the action of the wedge is in some sense topological. Actually, I'll jump ahead a little and come back. Topological in the sense that the action of the wedge can be replaced by a topological term. And this topological term has been observed in paper earlier, and it exactly ensures that the bulk computation gives you the correct G-function dependence from the ensemble of BCFT perspective. Going back, I wanted to show that you can have a very complicated wormhole, which in this case is one connecting one BIJK, a DII, a DJJ, a DKK, and a CIJK. And that computes the fifth moment of these complicated data. So it's a statistical ensemble that mixes all these different variables in a complicated way. And there are even more complicated wormholes, but what we do is sort of a little abstract, so we don't have to check case by case. We can argue that they all essentially reproduce the correct answers. This I already explained. From the BCFT point of view, you have some G dependence you want to reproduce, and that's essentially reproduced by the fact that the brane is topological. So gravity in this case does give you exactly the correct answer. We didn't completely prove that because we proved the case without kinks on the brane, but you can now have kinks and punctures. So the proof that this topological nature is more complicated. We did some checks. It'd be nice to check more or try to get a proof for that. Okay, so I think that was the hardest part too. That was the main part of the talk. So let me pause and see if there are questions.
So actually, I had a question. So I wasn't sure if I follow what was the difficulty. If you go back to the boundary OPE and the wormhole for that, you had a solid cylinder with So I guess I didn't understand. So it looks like you have a tension constant in each of the little a, little b, little c regions, and this jumps, right?
Yes.
So you get to put in 3 different tension, is that right? In the boat, or you only?
Yes.
So is there something non-trivial about that matching, or is that trivial? That
I think it's non-trivial in the sense that, for example, if I modify the action for the kink and the brane, I can easily get a mismatch between the bulk and the boundary. So it is some nice feature about this particular choice of the action, which I didn't write down, but it's a nice fact about this particular choice. It's also actually the natural choice, so it's not that we had to engineer very hard. It's a natural choice about this action that ensures that when you tune the tension of these different pieces individually, and the solution will change. It's not that we fix the geometry and change the tension in a trivial way. The solution will change because with different tension, they're all dynamical objects. This manifold will look like fatter in some sense, and each individual part will will have to be solved. All the solution equations of motion have to be solved to find a new solution. And however, the change in the action is turns out to be very simple, so that it reproduces the boundary expectation exactly. That was the non-trivial sort of part.
I see.
So by tensionless brane, do you mean like an orbital plane or something like that?
So sorry, can you say again?
Oh, so by saying tensionless brane, do you mean like an orbital plane because the junction condition on the brane becomes trivial in the tensionless limit?
I would say no, but maybe it's related, but I would say no, because here I'm only saying, maybe I'm using the word in a different way. I'm only saying that take the action of this brane and set this t to 0. It's still a classical object where now you can, actually a feature I didn't mention is that if you set the tension to be 0, you can obtain the solution by taking a Z2 orbifold. Maybe that's what you're saying. And if your tension is non-zero, you couldn't do that. So you have to solve the dynamical, all the equation of motion to find the location of the brane, the kink, etc. And that makes it more complicated.
Nice. Thanks.
Yeah. Okay, thanks for the question. Yes, any other questions? Okay, so since I essentially managed to talk about the main part, which is these classical wormholes. I of course didn't give all the details, but let me quickly summarize here. Is that we constructed a 3D gravity model with all these objects, and naively it's very hard to know what action you would want and why it would reproduce exactly the same results as bootstrap would give you, but we sort of reduced the problem into some simpler problem by realizing a topological nature of the brane, so that you can make the construction wormholes easier. And then, roughly speaking, we map all the problem into the case without end-of-world branes, and then that allows you to consider arbitrarily complicated wormholes without worrying about the details, because abstractly it has to work automatically. So that was the main reason why it works. And the topological nature was sort of a good, important step for this to make sense. Okay, I think I have maybe a few minutes for the finite central charge part. This part I will just say what we did without trying to explain, exactly why it works, etc. But for people familiar with the story without the end-of-world branes, this part is sort of easy to explain. So I'll only take maybe 5 minutes to say this. So I find it easier to start with a tensor model rather than the Virasoro TQFT because this is, as I was saying earlier, one way to construct or to see how a Virasoro TQFT arises from 2D. So here, the new tensor model would have to involve the same objects as before, the conformal weights of the bulk operators created by the spin. So essentially, this is H and H bar. And now we have the new spectrum, HI, capital I. We have the three boundary, three OPE coefficients. And there's an A, that's a technical thing, so don't worry about that. Essentially the same as D, but with the second index set to the identity. And now we have a potential that depends on all these data, and we want to write down that potential. So the way we do that is the same as before. We look at all the bootstrap conditions. Now there are 6 of them. We square each of them. We add them in to form this potential, essentially. So what we get is a open-closed TQFT. Before actually talking about 3D version, let me give you a simple example, which is the 2D story. So now imagine you have a closed TQFT in 2D. What you can do is to write down partition function on some manifold with some genus and boundaries, etc. And now if you want to compute the partition function on a more complicated geometry, you just have to glue them, because it's a TQFT. You can glue with the correct rules, you can obtain the partition function on arbitrary Riemann surface. So by the way, in this case the TQFT is 2D, so it's not related to the BCFT or the CFT. So if it's a closed case, you can glue along any closed circle essentially, and that gives you the new geometry. So to make it into so the open case, we should the new ingredient here is that instead of having to glue along two entire connected components or entire circles, you can glue along two intervals, which in this case would be these purple intervals. Once you do that, the remaining part of that circle, the blue intervals, they become joined, and they are just stay there after you glue the purple intervals. So now they become a circle. And there's that circle in our language is an end of the world brane. And from a string theory language, we can say that the first picture represents, closed scattering to a closed string, and then we glue that to another closed string. Whereas in the second picture, we say there's a scattering from closed string to an open string, and then we just identify this open string together, and that leaves a boundary where the open string could live, and which we now call end of the world brane. So that is the 2D story. There are many different ways to say it, but that pictorially, this is one way to understand it. And it's harder to visualize, a little bit harder to visualize this in 3D, but what I'm claiming essentially is that this 2D BCFT bootstrap give you a 3D open-closed TQFT. I think this part I might have to skip. It's a bit complicated, but roughly speaking, what we do is we look at some conformal block decomposition on the disk, for example, and deform these conformal block lines into a manifold with end of the world brane. And now we can work with those and etc. to obtain the 3D manifolds, which now involve the end of the world branes. So doing that procedure gives us partition functions on 3D manifolds with end of the world branes and a boundary Wilson lines, which are the analog for earlier we had bulk Wilson lines for which in the classical limit become conical defects. We now could have boundary Wilson lines which live on the end of the world branes, which in the classical limit become kinks. So here the story is just that working with BCFT, you get manifolds with end of the world branes, which are in some sense a quantum Virasoro TQFT, but it's open closed because the presence of this end of the world branes, essentially analogous to this 2D example here. And this would be one of the example. Let's see what that represents. It has 3 asymptotic disks, so it computes the bijk to the 4th moment. And because of these, each interval can have different boundary conditions. We actually have 4 end of the world branes with different labels. And in the classical limit, this label corresponds to different tensions for the brane. And just to show you that all these bootstrap conditions give you a lot of complicated geometry, this is the full set of bulk manifolds you need to now include These are the analog of the 6J manifold, etc. I was talking about earlier. With these, you can now construct the partition function on any 3D manifolds with end-of-the-world branes. And that was the story. I think I'm going to essentially stop here, but maybe I'll spend 1 minute talking about the summary. So the main takeaway, I guess, from the large C story is that the Tadashi's model is actually very good. The naive action you write down turns out to give you a topological, turns out to have a topological nature that exactly reproduces the boundary G function dependence. And of course, it's not just that. Everything you compute, including boundary operator, correlator, etc., gives you has an agreement with the 3D model we construct. And the finite C version, the main takeaway is that we get a open-closed TQFT. I didn't actually go into the detail of the tensor model because there are also off-shell geometry, etc., just like the tensor model. They already constructed, but everything is sort of analogous. That was the story. So some open questions. I guess we now sort of check bootstrap DV predictions for at every order. You could compute the quadratic moment, chaotic moment, etc. But is there a way to do it very systematically or even abstractly for an arbitrary number of correlators? I guess that's open, I think. And maybe from the tensor model point of view, it will be very interesting to actually study that model more carefully, try to see if you can match some computations. And offshore geometry, I didn't say too much, but because the tensor model gives you predictions for them, it'd be nice to actually do an honest calculation, like the Collar-Jensen computation of the wormhole, the torus wormhole, and see if there is exact agreement. However, I guess part of the difficulty for that is actually kind of subtle because of non-trivial mapping class group for offshore geometries. And understanding that could be an important step in trying to understand this the general story. And finally, a very recent work uses TQFT to study triangulations of a CFT. Essentially, you take a CFT, you triangulate it into little triangles, and where these triangles meet at the corners, you remove a little hole, and that turns into these objects into BCFTs. And then you can use TQFT technology to study these triangulated theories. It'd be very interesting to make further connection between this work and try to understand the story better. I think I'll end here. Thank you.
Are there any questions from our Zoom audience out there? I wasn't very good about keeping track. I have questions, but
I can ask a question.
Why don't you go ahead? Yeah.
Hi, yeah, thanks for the talk. So maybe you said this, but I didn't quite grasp it if so. So you have lots and lots of components of your potential, and you map each of these to building blocks of the manifold.
Yes.
Do you directly demonstrate that all of the things that you can build out of these Lego pieces are all the manifolds that you want? Or do you just say, we assume that these are all the manifolds that we want in the dual gravity theory?
Good. Well, that's a very good question. So we sort of didn't do it explicitly, but we know it works because essentially because the Moore-Seiberg or the Moore-Seiberg theorem, saying that all these 2D bootstrap conditions are sufficient But then you have to turn that into a 3D language, which I don't think is totally clear to at least not in their original paper, but with the technology and with the understanding of the relation between TQFT and CFTs, for example, the WZW and Trans-Salmon connection, it seems to be understood. And so using that connection, I think the answer is yes. In the closed case, where, in the closed case, Gabriel and others already sort of can do it explicitly in the bulk. So in other words, even if you don't assume that connection, you can also check it explicitly. I think here, for us, we didn't check it explicitly. I mean, we could try to do it, but the reason why we know it works, we do obtain all the manifolds we want, is because of that connection.
Thanks.
Yeah.
Can I ask you a question? So in 2D, there's this beautiful characterization of open-closed TQFTs in terms of algebras. When you have a closed TQFT, it's Frobenius algebra. The open TQFT is another Frobenius algebra. And then when you combine the two, it's another. So there's something called a knowledgeable Frobenius algebra. That's like a real name. But that's like the particular algebraic structure of a TQFT. And you can write down a finite set of generators. They're like the building blocks, but maybe more strict than what you call building blocks, because they're like these cobaltisms where cobaltisms only glue in a certain way. They're sort of an arrow of time. So only incoming boundaries only glue to the outgoing boundaries. I never understood whether in 3 dimensions there was such a precise definition of an open closed TQFT, like where or maybe say differently, and usually people say in 3D TQFT, it's a modular tensor category. That's what they say. Is open closed TQFT something like a generalization of a modular tensor category, or what's the right framework?
That's a very good question. So in some sense, I believe it has, at least the rational case has been done like quite in details. So the people studied the open-closed analog of the modular tensor category, and I actually don't know if that's the same as what you call knowledgeable, but they had to modify the structure by taking into account of all these new bootstrap conditions for rational CFTs. So in some sense, we could have followed that approach and obtain everything systematically using the tensor category perspective. But it is personally very difficult for me to understand that. But secondly, the picture is slightly different in that they don't have the end of the world branes, because they, roughly speaking, take a double cover of all these manifolds. So in the language of the pictures I drew earlier, you take 2 of these diagrams and glue them along the branes. So you then only obtain closed manifolds. So in that sense, most of the story is similar. But one thing that would be missing in that language is the dependence of the end of world brane tension and the G functions. So they are working with a rational CFT. They don't have the same problem. But for the irrational case and for the 3D gravity analog, I think this is an improvement. But of course, in terms of rigor, this is definitely not as rigorous as formulating it in that language.
I see.
Yeah.
Any other questions? If not, so I have more questions for you, but I don't want to keep everybody here. So I'm gonna let's give you another round of applause. And thank you very much for being the guinea pig for the first seminar. I'm hoping there'll be many more, and I hope we can chat actually much more about this. I think this is very good work. Thank you.
Thank you very much, and thank you for coming, everyone.
You're welcome. Okay.